So starting with clutches. So the one which you can see on the left side is a clutch. Clutch is essentially a mechanical device, right? So it is used to connect or disconnect. So here you can see it is connecting and disconnecting. This is at the power of the operator. So at the will of operator. So whenever you want it to engage or disengage, so it is at your command. So it is used to connect or disconnect from the source of power. So usually, so this will be connected to drive shaft, okay, from the engine, and whether you want to change gears or connect it to the power transmission system, that is to your wheels. So mostly it is used in automobiles. It's also used in power presses and farm equipment and all those things. So this is desirable when the engine is to be started or stopped, or whenever you need to shift gears, right? So that is when you use clutch. You may have a practical experience of this also. Some of you might. So very often you have three terms which come when you are designing or just driving a vehicle or something. So you have couplings, clutches, and brakes. Couplings, which we have covered in the last semester. The couplings is sort of a permanent connection, right? So whenever you are driving, the driven and the driver members, it's a permanent joint. So whenever you want to connect two shafts which are permanently connected, like the transmission shaft and the one near the differential, so these things are permanently connected. Oldham's coupling, then knuckle joints. So all these are examples for couplings. Whereas if you see clutches on the other hand, they are different. Okay, they can engage and disengage. They are not a permanent joint as couplings. So all these are used in transmission. There is couplings, clutches, and brakes. Only couplings here are permanent. Clutches and brakes, they are temporary engagement. Then how do you differentiate between these clutches and brakes is depending on the initial and final condition. Okay, if you take clutches in the first case here, in the initial condition, you can see the member here is at rest. So this member here will be at rest. Okay, whenever you engage, so this is the initial condition. The driving member is rotating here, and the driven member will be at rest. When you see the final condition, once it is engaged, both members are rotating at the same speed, right? So initial condition is driving is rotating, driven is stationary. Final condition, both are rotating. Whereas if you see in brakes, no, the initial condition is you have one member, that is or the brake drum will be rotating along with the shoe. So along with the brake shoe, it will be rotating, and the final condition here is both will come to rest. Okay, that's how you differentiate between the clutch and brake, right? So uh, here one is stationary, one is moving initial case. Here both are moving in the initial case. Final condition, both are rotating. Here both are stationary. So that's the basic difference between a clutch. So both are used in the transmission system, and both are in your control. That is with the will of the operator. So that's where it lies, right? So let's start off with clutches here. So definition of a clutch. So we are starting off with clutch. If you want to define a clutch, and define it as a mechanical device used to connect or disconnect from the source of power from remaining parts of the power transmission system at the will of the operator. That's how you define it. So you connect or disconnect from the remaining parts of the power transmission. You can see the engines which are constantly running. You can't you know connect directly the power drive shaft to the engine. You cannot connect it directly. Okay, so you need a transmission system, or you can call it as a gearbox or anything. Okay, so to change the speeds and stuff, so you have multiple gears in a car or a bus or anything, right? You can't connect directly this drive shaft to the engine, because will directly affect the engine speed, will directly affect the movement of the drive shaft, right? So therefore this clutch is in place. Okay, so it connects and disconnects at the will. So whenever you're shifting gears, or you want to stop the vehicle without shutting off the engine, right? So in those cases your clutch comes into picture. Whenever using in engagement or disengagement kind of operation you need with the transmission system, so that time you need a clutch. And brake is the opposite of that. So you're already in motion, right, and you want to bring it to stop, disengage the clutch and engage the brake. So that's they both work in tandem, you can say, right? So if you see clutch, there are a variety of parts. There's not a one single component here. So there are a variety of parts. The first to start with, this is a typical drive system. So engine connected to the flywheel here. So flywheel will be rigidly bolted. So this clutch will be rigidly bolted to the flywheel, and you have this friction disc. Okay, so this friction disc is what is connected to the transmission shaft. Transmission shaft, which is in the which goes into the gearbox. Okay, you have a you can see a hole here, a through hole which goes till this point. So this through hole will be splined. Okay, it will be splined, and this is what transmits the motion from the flywheel or from the engine to the gearbox, and in turn the transmission system, and moves the vehicle. Okay, so this clutch is rigidly bolted, and usually here we'll have the friction disc, which gradually engages with this clutch disc and enables movement, gradual slow increase or a gradual increase in the speed which is being transmitted to the drive system. It's a combination of parts. And if you want to see the positions of first, it's important to understand what the very basic arrangement looks like. Okay, this is an example of a single plate friction clutch. Friction clutch, where it consists of two flanges. So one here is stationary, and the one on the other side is movable. Okay, so this part is stationary, and this is movable, which is in the driving shaft, right? So this is connected to the driving shaft, and this is a driven one. So this is constantly rotating. So this is connected to the flywheel and is constantly rotating, and this will have a lining of friction. Yatish, your raised hand. Have a doubt? You can type in your queries. You have right. Have any doubts? You can uh, post it in the group chat. So this is a friction lining. Um, when this is a rotating member, this is a driven member, which means this will be driving once it comes in contact. So this in turn is connected to the uh, operator inside the vehicle, or it's an operator somewhere else. So there will be a lever connected to this, and you can see this shaft here is separate from this. You have two separate shafts. So this shaft is splined. You can see here the grooves. So if it is splined, what is the advantages? It allows axial movement. You can see the arrows point to the direction. You can have an axial movement, and this spring provides a pressure, so uniform pressure to press this flange against the friction lining here. Right. So you can press this flange onto the friction lining, and thereby can achieve rotation of this also, and this motion transmitted to the spline shaft. The spline shaft again transmits it to the gearbox or the transmission elements. That's how it works. That's the basic operation. So this is a little bit complex representation, but it's all the same. So when it's engaged, right? So when it's engaged, so you can see this plate here. It comes in contact with the flywheel. So this you can imagine this black part to be which looks like a fork here, no? You can imagine this to be a flywheel, and this has a that clutch plate. So clutch plate is rigidly bolted. You can imagine that as this particular figure here, and sometimes the friction lining will be on the second flange. So you can call this entire thing as the second flange. So second flange, when it comes in contact with the first clutch plate here, so then you have transmission. You have that rotation of the shaft. So until unless it comes in contact here, this will be stationary. This part will be rotating. So is in disengaged position. So whenever you're shifting gears or no, you don't want the vehicle to move, it will be in disengaged position. So when it engages, when the lever pulls, right? So you this springs, you can see they're elongated and they come in contact with this clutch plate, and in turn both are rotating right now. So this is an engaged position, and now you're transporting or you're moving the vehicle in that kind of application. So if you see the classification of clutches, right? So they're classified into two kinds. So one first kind is method of engagement, how you are engaging, and the second method we'll discuss next, which is the clutch element. Okay, whether it is positive or friction clutch and all those things. So first method, let's say the method of engagement. So method is by mechanical you can engage. Mechanical in the sense it is friction or a gear type arrangement, okay, which have teeth and stuff. Second one is pneumatic or hydraulic, which will have a fluid, okay, fluid based engagement. Then electrical. So electrical just means that using some eddy currents for those kind of stuff, and finally magnetic, using some ferromagnetic fluid or even some magnetic flux kind of a thing. So all those things are uh, again depicted here. A positive contact, you can see there are jaws, so just like gears meshing, right? So gears meshing to each other. You can imagine the jaws also meshing is normal to each face of the gear, and you can see that it meshes and motion takes place. If you come to friction, so far whatever examples I've shown before, right? So all were friction based. You have a lining of friction material. Okay, so those material uh, would be lined, and it can be in form of disc or it can be in the form of a drum or even a cone. Right? So these will discuss the next slide more elaborately. So overrunning type, you have three more. There is roller, drag, and spring bounded. Magnetic, if you have magnetic particles or hysteresis or eddy current type, some ferromagnetic fluid type, and finally fluid coupling. Maybe it's dry fluid or hydraulic oil pumped or those kind of things. So for our subject point of view, we are going to see only this friction clutch. Okay, friction clutches. Mm. This classification is a simpler version, and this is what you need to keep in mind. So this version is more than enough for you in this stage. They have two main types in types of clutches. This is based on engagement, okay, and not based on not engagement. This is just a type of material use, type of overall physical appearance. So you have two types. One is positive, and another one is friction clutch. The friction clutch is what we are going to design in this semester. So mostly two types of these. So positive clutch. Positive clutch, it just means that it is you know this is a positive clutch. You have teeth which are protruding out of the face of this two cylinders here, and they engage. So as you just push one, it's simple. It's just like a gear. It's like a gear which is in a pressed position. So where these are used is very mill operations. You can see that mm, you can see these kind of gears in mill and in very slow speed applications. Very you know, when you want to operate in very low speeds. For example, in power presses. So power presses, you have a big flywheel which is running at a low speed, and you want to engage onto that drive shaft, which is connected to that flywheel. So in those cases, you use this uh, what is this positive clutch. Okay, you can't use this in high speed because obviously shocks. Okay. And you can see it's not also gradual. Once it's you can engage only in slow speed, impossible in high speed. So most uses will be power presses, the sheet metal power presses, and mills, rolling mills, kind of operation. So that's about positive clutch. Not going to design that, but we are going to design this. This is a single plate with friction clutch. That is the second type. That is coming to friction clutches. We have the first one, plate or disc clutch. So this is a plate clutch. So you can see a plate which is engaged here and is being pressed onto the clutch. So this will be the flywheel, which is the driving member, and you have the friction linings here, and you have a small thin plate which is acting as a spring essentially. And so whenever you press, so it presses and disengages. So that's how you control. So this lever is what used to control. You can put a small disc here and take it for the automobile applications like that. So that's about a plate clutch friction. So again, in all these you'll have the lining of friction inherent on it. So all these clutches, they use a layer of friction, can be replaced. And so you have in plate clutch you have single and multi plate clutch. So what I showed you just now is a single plate clutch. You can also use multiple plates. So this is a plate clutch which is using multiple plates in between. So you have compressed strings here, and you have a spline shaft which is running inside of this shaft. And the brown ones which you can see here, they are all the linings. That is the friction material linings. And like this plate, you have several plates in between. Okay, so you have several plates in between which are contributing for that coupled action. So these are used for gradual engagement and for very high speed applications, and race cars or those kind of stuff. Very high speed applications in automobiles basically. And more number of plates means increase in mass, and but you have a better control over speed and other things. So next you have the cone clutch. Cone clutch, it is just the clutch plate, it is in form of a cone. Okay, and you have the lining of friction in entire surface. So you're increasing the surface area of the lining, the friction lining, whatever is there. So you're just increasing the area here. Okay, and you have the flywheel also in the shape of a cone. Okay, so advantages, you have a bigger surface area which can engage better, can engage better, and also exit from it better, uniform fashion. You can enter and exit in a uniform fashion, and engage and disengage in a much uniform matter, I can see. Again, here you are using the spline shaft to engage and disengage. And you can see here the friction lining, which is mating with this flywheel here, which is also in the cone shape. So finally, you have the centrifugal clutch. The centrifugal clutch is just like a drum brake. you have come across the drum brakes, right? So it goes similar to the drum brake. So you have this is like the front view of flywheel. You have the housing, and inside you have these friction lined blocks here. So whenever you engage, so they come in contact with the flywheel here, and this in turn is connected to the engine shaft. Engine shaft. I think this is with the flywheel, but the ones in the blue, the blocks, no. So whenever they come in contact, they transmit this power from the engine shaft or the flywheel to the transmission shaft. So that's how these centrifugal clutches work. So these are used whenever you need to make the vehicle compact, no? Very small. You want to reduce the size of vehicle overall length. You have some restrictions. So in those cases, you can use these centrifugal clutches. So they are not that common. So that's it for the classification. But we are going to design here only plate clutch and cone clutch probably. So plate and cone clutch we're going to design, and after that we'll just move on to the brake portion. No advantages and disadvantages. I think it is inherent. So you can see here the section view of the positive drive clutch. You can use either square jaw or you can use spiral jaw. You can see the jaws here, which are gradually engaged onto the flywheel. And this is the blue ones. The right side ones are the one which connected to the transmission shaft, and the left ones are with the flywheel. So advantages are it is simple. There's no heat generated because direct engagement and disengagement. There's no slip as in case of friction. They're compact, very simple to manufacture, and because of their compact, they are also low in cost. The disadvantages is it must be connected when shaft is unloaded, meaning if you are moving this to an engaged position, no, this shaft should not be loaded or it should not be rotating. So only you can. That means you can use only in low speed applications. So as I said again, power presses only those are running in low speed or intermittent motion. So components, if you want to see, you have three members in a component of plate clutch. You have the driving members, which is the flywheel and this housing here. These are all driving members which are connected, and these will be rotating as the engine rotates. Okay. And the driven member, usually this will be connected to the transmission shaft along with the spline shaft. So this is a driven member, and the operating member. Operating member is where used to engage this particular driven member to the driving member, and you can shift gears and you can move the vehicle and all sort of stuff. So just like a gear, but reverse in operation. Now coming to the next, so that's about the introduction to clutches, and you'll have two derivations when you see this uh, single plate friction clutch. So friction clutch, you have two derivations which will be asked probably in your exams. Yeah. So this is an important derivation. About you'll have about 7 to can be asked over 7 to 8 marks, or even standard for 10 marks. So just check this out. I'll just go through the derivation here. I'm not typing anything today. So this is your clutch plate, which has a friction lining. Okay, so here in this clutch plate, we assume a small infinitesimal area. Okay, so later for integration purpose, we'll assume only a small circumferential area here, cylindrical kind of an area, okay, which has a mean radius as delta r. So this entire contacting surface can be said as this. So this is essentially a hollow cylinder kind of thing. So hollow cylinder, therefore surface area will be as pi times r1. The bigger circle is r1 and the smaller circle is r2. Square of both, and you subtract. Using this boolean, you have just the area, and r1 is external and r2 internal, and r is the small elemental ring. So this, since this area what we have taken is very very small, no, so we'll have only one r. We won't have small r1, small r2 here. So let's have only small elemental radius here. We analyze what's happening here. Okay, so analyze what's happening here. So the objective is to find the torque transmitted. Okay, so in order to design the dimensions here in the data handbook, we need to balance the torque. What is the torque required to transmit, and what actual torque you require to move this plate. So that's how we move on this. So some more terms with this derivation. The area of the ring on contacting surface, see delta r, only a small elemental area we are talking about. So it is 2 pi r is circumference, and times that radius. So that is the entire area of that small part. And axial load, you see, which is on the ring, again on that small area, is pressure times area. So load is pressure times the area. So P is the pressure acting on that particular small area. Then frictional resistance offered is again frictional resistance is nothing but frictional load, which is mu. Mu is the coefficient of friction that of that lining, the friction lining which is there, and that small load which are applying. Okay, so it's coefficient of friction times the load which are applying on the ring. So together expanded, it is 2 pi mu p r and delta r. Okay, so next, frictional torque acting on that particular area is you can call it as T, which is equal to force times the radius. Force times the radius. The radius is we'll just put it as r. So r times r will be r squared here. So everything here will be just put here, just multiplied by r. So this we keep it as equation 1, because from here it can go two ways. Okay, from here you can define it on two bases. So till here, as I told you, there are two derivations. So till here it is common for both the derivations. So this step, this entire slide is common for both steps. Okay, so whichever derivation is asked, you need to do till here, name it as one, and then you need to split into two derivations. Okay, so very simple. So from there, as I told you, you can assume two theories. You can assume two theories. That is, either you can assume that uniform pressure is acting, or there is uniform wear across the entire surface of the friction lining. So let me go back to the figure and tell you what it is. So here, in this entire friction lining area, I can assume two things. I can assume that pressure here is acting uniformly across the entire area. So this is the face, right? So on this entire face, this is the front view. In the side view, it will come over here. So on the entire face, I can assume that there is uniform pressure acting, and in that case, I cannot assume uniform wear because the radius is different at different locations. You can see more wear as you go outside. Okay, the friction lining. So more wear here, and as you come inside, there will be lesser and lesser wear. Okay, so when you assume uniform pressure, there won't be uniform wear. And second theory is uniform wear. So if you assume uniform wear, then you can't see uniform pressure because pressure will increase as you come inside. Okay, so pressure will be more inside, and as you go outside, it will be lesser. Okay, so that's the two theories. Okay, either you can design based on uniform wear or uniform pressure. So equations are different for both. Hence, you have two different derivations. So this data usually will be given in the problem. Assume uniform wear or uniform pressure. This data will be given in the question, not to worry. So from derivation point of view, so we have two different. So till here I told you it is same for both the derivations. We keep it as equation one. Here this data will be given, either assume uniform pressure theory or assume uniform wear theory. This will be, okay. So if one is constant, other will be variable. That you have to keep in mind. If pressure is constant, and wear will not be constant. If wear is constant, pressure will not be constant. So that's what we keep as a base for deriving this equation. So if you assume this uniform pressure theory, then what you're doing is you're keeping the pressure constant. So the pressure is distributed uniformly over the contacting surfaces. That means the pressure is nothing but load over the contact surface area. The contacting surface area is this thing. So the entire the hollow cylinder formula. This is the contact surface area. Then total torque will be integral of 0 to t and between R2 and R1, and this is the torque. There is torque which is from equation 1, which is defined this, right? So P we are taking outside because since we are told P is constant, right? So we are taking it out of the integral and we are just integrating this radius with respect to dr. And once you differentiate this, so you'll be getting an equation in this fashion, that is r1 cube minus r2 cube in this fashion. And then P, anyway, now we have defined what is that pressure, the generalized formula. So this generalized formula is substitute in the same form, and simplifying you will get this equation. So this equation will give us transported single plate clutch due to friction. This is considering the uniform pressure theory. So this equation is there in our dead end. So I'll tell you the exact number when we go to the steps. Okay, while defining the steps required. So that time we'll just define. And this equation is for uniform pressure theory. So it is specifically mentioned in the dead handbook that this is the equation. So you just have to work backward. So for P, define this and just plug it into the P by taking P as constant. That is pressure as constant. So that's about uniform pressure theory. So same thing happens when you go for uniform wear theory. So in wear theory, so PR, that is the wear force, pressure into radius, force is constant. So P is equal to constant by this value R. So we'll keep this and then define the same thing. So we know axial load in the ring, which we defined before, is this particular equation here. P you just replace by C by R. So if you replace by C by R, you'll get in terms of load, the small change in load, which is for the elemental area. So that we'll get it here, and integrating within the limits. Integrating within the limits, this load here, you can take this constant outside and only the radius you'll be integrating, and you'll get C, that is a constant value here as this particular equation here, because C you can't just substitute, right? So this value of C, you need to get it out of this load and radius and stuff. So once you have defined the C, we can go back to that equation 1. The equation 1 which we defined in the first uh, first slide, right? So write P in terms of C by R. So since here the pressure is not constant and it is dependent on wear, so define on this and then again integrate this equation, okay, with respect to the radiuses. This is to get the torque transmitted. So C is constant, you can take it outside. P written in terms of C by R, 1R remains. And once you expand, you'll get the final equation in this fashion. And this is for uniform wear theory. Okay, you can see this is pretty straightforward, right? So entire surface contracting. That's why you multiplied P into R, which is a constant, and then you get this equation for torque transmitted by uniform wear theory. So you have uh, these two divisions here, okay, uniform wear and uniform pressure theory. So that's it for the derivation. Then this will be asked for either 8 to 10 marks, somewhere between 8 to 10 marks. And it continues. Here C, if you have plugged in, we can use this equation. I don't think it is in the data handbook. So what happens is C, you're just substituting here and just finalizing. That's it. So once you substitute in that equation and simplify further, no, you'll get a final equation which is not having that value of C, and this equation you need to keep in mind. So this is for uniform wear theory. Again, this is on in the data handbook. It is a little bit lengthy. Why? Because you have to give a new value C, and then you have to define what value C means. That's why a little bit lengthy. I think maybe this will be for 10 marks. So yeah, this is without that value C. Now, this is torque transmitted using without with considering uniform wear theory. Power transmitted, I think you know this. Power transmitted 2.0 by 60. This we have been using since yes, it is in watts. Usually this will also be in kilowatts. It will be 60,000. Right. So that's it for the derivations. Two derivations, which will be one of which will be definitely asked in your exams. You need to prepare for this. Mark it as important. Both these derivations are important. So in multi-plate, no, you just have multiple plates. So as I showed before, you have multiple plates here, which is connected in between the shaft. This is for better control and faster engine operation. So when you engage all these, you need to give some artificial cooling and all those things. The heat generation also drastically increases. Increase the plates and stuff. So you have this entire casing which is cooled. So you see these pipes go in, which are used as a cooling for cooling purposes. You have liquid going in and coming out. Another pictorial representation of how these plates are. So these multi-plates, you can use multiple plates. That number also depends on torque transfer. More the torque transmitted, more will be the more will be the number of plates, and you can see they are completely enclosed. So completely enclosed means have some kind of coolant or something circulating inside of this. The applications of this multi-plate friction clutch, you can use it in heavy duty machine tools like CNC milling, CNC lathe machines, and industrial marine gearboxes completely enclosed in water, automotive transfer gas in high speed machinery, agricultural machinery, big machinery like the harvesters, combines, and stuff. Even tractors, where torque is very much required till the soil, right? Okay, so that's it for the application part. So we are starting off with designing of plate clutches. This is a procedure, a very brief procedure for designing this plate clutch. You can just take a screenshot of this. So step one, we find torque. Okay, power will be given usually in the question. So we need to find the torque here. So using this equation, we find the torque, and then using the torque and whatever permissible shear stress, again tau permissible is permissible shear stress, so sometimes which is dependent on yield stress and factor of safety. So this equation is standard. We have used this multiple times in DME1. I hope you remember. So use this and get the diameter of the shaft. So this diameter of shaft is the diameter of the spline shaft connecting the clutch plate, right? Connecting the clutch to this with the transmission shaft. So that's the diameter of shaft. This equation you can also find in shafts, the chapter shafts which you have in the data handbook. And for this, data handbook will be for clutches which we are using. No, that is Mahadevan. We won't be using Lingaya for this. Again, we are following up with Mahadevan. The soft copy I have uploaded already on Edit. You can find it and download. So this equation will come under shaft. If you remember, well and good. Otherwise, you need to look this up in the data handbook and mark it up, right? And this equation again used multiple times. This is to calculate the diameter of shaft. You will get diameter from the step 2. Very few steps are there, you can see. So step 3 is you get the mean diameter of the lining. So mean diameter of the friction lining, assuming whichever theory is given in the question, either uniform pressure or uniform wear theory, whichever theory is given. So that particular theory you assume and then use that to get the mean diameter. Okay, mean diameter of the friction lining, what is required. And then the fourth step, the force required. So what force you need to apply so that you engage, you apply that particular pressure onto the clutch plate. So again, this is differentiated based on the which theory you are using, uniform plate or uniform pressure or uniform wear theory. Whichever theory you are using, again the formula will differ accordingly. Right. So this talks about the axial pressure. This talks about the axial pressure. Oh, I forgot to put animation for this. Hold on. Okay. So step 3, I told you about pressure. This is to find the mean diameter of friction lining, and this is step 4, used to find the axial pressure in case of uniform pressure and uniform wear theory. FAW is a force in axial, and you're assuming uniform wear, right? And next step, what? Okay, so this is step 4. Axial force. It is same step. So the axial force only this P max. The max pressure for that particular material. Only for that you have this table. 13.4 friction material. So depending on friction materials. So what the contact surfaces are, how wet or is the surface dry, and depending on temperature. No? So you have maximum pressures here in meganewton per meter square. Again, nothing but Newton per mm square. So this is pressure. This value you need to extract. So if you have in between limits, no, you just find the mean of this and then substitute. So depending on what material and what coefficient conditions, then temperature condition. Depending on all these things, you need to just take the maximum pressure and you need to substitute here. That is the P max and extract the value. This is also P max. Extract that value and put it there. So this P is small p, which is pressure. Okay, not capital P, power. You just need to take small p here. Intensity, same table, 13.4, 13.4. So this is depending on two. You don't need to do both, only one. And the last step, you are just finding the torque transmission capacity. So out of all these dimensions, the mean diameter and the axial pressure, okay, and this n dash, that is pairs of friction surface. So depending on all this, you'll get the transmission capacity. And in the first step, you would have found what is the transmission required. So transmission, what you have in step 5 should be greater than or equal to what you get from step 1. That is from power. So what is required should be greater. Okay, so what is the capacity of this should be greater than what is required. So step 1 you get required, step 5 you get what is the capacity, and from this you will get the dimensions. So from this we can extract some parameters like d naught, d1, and n, which were not known before. Right. So yeah, that's it for the steps. Tomorrow we'll start off with the numerical. So any doubts in